So in this video here, we're going to be looking at situations that can be modeled as exponential growth or decay. So here's the generic form for an exponential function, y equals a times b to the x. You can also see it written like this, where the b is in parentheses instead of using the multiplication dot. You do need to know that it means the exact same thing. It basically just depends on whichever one looks better. And the reason why these are called exponentials is because you have a variable in the exponent, right? Variable in the exponent means exponential. So with these ones here, that this a value here, that's your start amount. It could also be like the y-intercept on a graph. And then the value that replaces the b, that's your growth or your decay factor, right? That's how much you are multiplying each time. Because remember, linear is where you're adding the same amount. Exponential is when you are multiplying the same amount. So remember with linears, we had y equals mx plus b slope-intercept form. That m, that's your slope or your rate. And let's just pretend it's 50 miles per hour, right? So that means for every hour, you are adding another 50 miles. Whereas like if b was a 2, that means you're multiplying by 2 for, using cars every hour, although that gets kind of crazy as you get faster and faster and faster. But that's the main difference between what we've been doing with linear and now exponentials, right? We have a variable in the exponent, that's exponential. In this video, we're going to be starting out with word problems or situations or scenarios. And from those, we're going to be writing an exponential function. And then after we have written our exponential function, we're going to be looking at different values in the future of what this function is going to model after, X amount of years or days or whatever it might be, or even minutes. In this example, we have a population of organisms. Now, this could be people or it could be bacteria. I think in our brains, let's just think bacteria might be a little bit easier to think of. Population numbers 15,000 organisms initially and increases by 1.9% each year, or 1.9% per year or every year. Now, this increase or decrease by a percent, that is going to be exponential in form. So we are going to be thinking y equals a times b to the x, where a, that's your starting value, and then the b is the growth factor. So with this one, we can start out, instead of a y, we'll use a p for population. The population equals, and then next up is the starting amount. We're looking at replacing the a with the starting amount, right? Well, it says here 15,000 organisms initially. Initially means starting out. So the a gets replaced with a 15,000. Now the growth factor is what we're going to figure out next. Now with these percents, it can be a little tricky, okay? So here we go. So remember, if it doesn't change at all, like if next year you have the same amount, then you're just going to stay at 100% of what you had last year. But here we're not staying at 100%. We're actually going to add to the 100% another 1.9%. So this is what we're thinking in our brain. But when we do calculations with percents, we don't. We change them to decimals. So this 100%, move the decimal place over 2 spots, is a 1, right? And then a plus, right? Because when you multiply by 1, it stays the same, which is what 100% does. And now, again, this 1.9%, the decimal is right behind the 1. You got to move it over 2 spots to go right there. And that's how we calculate growth factor with percents. We do 1 plus, and then the decimal of the percent there. So the growth factor is going to be 1.019 every year. So we're going to use a t for our exponent for time in years. So now that we have our function, we can actually go back and restate the question or the scenario just looking at the function here. Population starts at 15,000. And then every year goes up by a factor of 1.019 every or per year there, t for time in years, okay? Now we're going to switch it up. Instead of increases by 1.9%, we're going to decrease by 1.9%. Same as the very last one that we did, except here we're doing decrease. So remember, 100%, from this year to next year, if you stay at 100%, it doesn't change. But here we're going to subtract, or we're going to take off 1.9%. Again, we want to change those to decimal. So it's going to be a 1 minus 1.9%. So move the decimal place over, boom, boom. So it's 0.019. And now we do our subtraction. So our decay factor, the last one, it increase, so that was growth factor. This one decreases, so it's a decay factor. Anything less than 1 is decay, more than 1 is growth, right? So here we go. Population is 15,000, starts at 15,000. Then our growth factor, or in this case, decay factor, is 0.981 per year. And again, what this is basically saying is there is 0.981 remaining the following year. This example here, we have bacteria. It initially contains 2,000 and doubles every half hour. So this doubles, that means you're multiplying. You're doing some repeated multiplication, okay? So it's a doubling function, multiplying. So we know that we're going to be using an exponential function. So in this case, y equals a times b to the x, right? So a is your start amount. So we are going to start by looking to replace the a with its value, and then the growth factor in this case is going to be super easy. So here we go, right? P for population. Instead of a y, we use p for population. The p is a little bit more specific to the question that we're working on. So population equals, starts at 2,000, right? Initially 2,000, so starts at 2,000 times growth factor. Well, it doubles. Your growth factor is 2, right? And then this is going to be every half hour. So x is every half hour. Now, this one is a super simplified version. There are more sophisticated forms that we could use, but right now we don't have those tools in our tool belt yet to write the more sophisticated ones. So we're just doing the basic exponential function generic form, okay? So here we go. Now we're going to answer the question, find the size of the bacteria of the population after 4 hours. Well, here's the question. How many doublings do we have in 4 hours, right? So, well, maybe we don't know that. Well, how many doublings do we have in 1 hour? Oh, well, it says it doubles every half hour. So every 1 hour, we're going to have 2 doublings in 1 hour. So if we have 2 doublings in 1 hour, how many in 4 hours? That's going to be 8 doublings. And this is just kind of a way that you can think through these types of questions here. You might be, reading this for the first time going 4 hours. Well, it talks about half hours here. I have no idea how many doublings there is. So basically you just break it down. Well, I know every half hour is 1 doubling. So 1 hour, there's going to be 2 doublings, one at the first half hour, one at the second half hour, right? And now that I know that kind of the rate of doublings is 2 doublings in 1 hour, right? Which means 2 hours I'll have 4, 3 hours I'll have 6. Oh, in 4 hours I'll have 8 doublings, right? Or we can just say, 2 per hour times 4 hours, 2 times 4, that's going to make 8 there. So just kind of a way of thinking through some of these ones that might not pop into your head right away. Now that we know how many doublings we have, now we're ready to go ahead and calculate that out, right? So remember your exponent there, that tells you how many times it grows or decays. In this case, how many times it doubles, right? That's going to be your exponent there. So now we can go ahead and put that in there, right? It's going to double 8 times. So an 8 goes there. This one, because the numbers are actually pretty easy to work with, you could do this in your head, right? 2 to the 8th. You have 8 2's being multiplied, so that's 2, 4, 8, 16, 32, 64, 128, 256, right? And then times this 2 here is going to be 512, and then put 3 zeros on the end, right? And I went through really fast. If you know your powers of 2, you could probably do this in your head, or if you've played the game 2048 a bunch, you could. If not, you probably just go to a calculator here, right? So we're going to do 2,000 and then times, and then 2 exponent, and then an 8, right? And then you can hit enter if you want on this calculator. I mean, on some of them, it just starts showing your total as you keep going there. Either way, it's 512,000 bacterias in this case here after 4 hours. So same scenario here, except we're looking for 100 minutes. So when we had 4 hours, it was actually an even number of doublings. This one, it's going to be a fractional or a decimal amount of doubling. So it's a little bit trickier to kind of figure out, right? So here's our question. How many doublings in 100 minutes, right? Well, doublings are every 30 minutes. So how many 30 minutes are in 100 minutes, okay? So now that we have kind of this equation here, we think of the question mark as our variable, right? And then to solve it, we're going to undo the times 30, right? So how do we undo times 30? With a divide by 30. So 100 over 30 is the number of doublings. Now we are going to be using this fraction in further calculations. So anytime that happens, it is a really good idea to go ahead and reduce the fraction, right? So in 100 minutes, we're going to have 10/3 doublings, right? So we know we have 10/3 doublings in 100 minutes. Now it's time to go ahead and do our calculations, right? So the variable, that's the number of times it grows. How many times does it grow? It grows 10/3 times, or we're going to have 10/3 doublings. And now it's time just to go to the calculator and calculate this out. So check it out. So here we go. So we're going to go 2002,000 times 2, and then exponent, and now we got to do 10/3. So you can either do 10 divided by 3, or you do the 2000 times 2, and then exponent, and then you can hit this fraction button here, and then you make sure you're in the top, the numerator, hit a 10, and then arrow down for the 3 there. Either way, it'll get you this answer here. If we're rounding to the nearest whole number of bacteria, because normally we don't have fractional ones, that would be 20,159. So if we're rounding there, so that would give us the number of bacteria after 100 minutes. And again, you're not going to have an even number. So there's going to be some rounding involved there. So remember, on these exponential growth or decay, our generic form is y equals a times b to the x, or the b can be in parentheses. It just depends on whichever one looks better. The a, that's your placeholder for your starting amount or your y-intercept, and then the b, that's a placeholder for your growth or decay factor. Now, remember, with percent increases, that's going to be 1 plus the percent for your growth factor. And then if it's decreasing, you're going to subtract from 1 and again, we change the percents to decimals when we do that to find the decay factor. So anything more than 1 is going to be a growth factor, and anything between 0 and 1 is going to be a decay factor. And then when we're trying to figure out, like, in the future, how much is the bacteria going to be, the population, that's going to replace that x only for when you're calculating it out. So if you're just writing a generic function for it, that x is going to stay a variable. But then when you go to figure out, like, okay, so how many doublings, or after how many hours or minutes is this bacteria going to be, that's where you're replacing this x with a value.